Good morning, everyone. I can see many people I know here. Hello, everyone. Okay,
Hello, good morning.
so it's almost time to start. I will give everyone a couple of minutes to join and then we'll be off. Okay, 11. It's 11. It's time. So let's start. So good morning, everyone. I'm Pascal Bernier-Brunner. I'm the EUPEX communication leader. And welcome to this second EUPEX webinar. So, sorry, I'm trying to get to the next slide if it, yeah, okay. So, second webinar because it's one of a series. EUPEX is a EuroHPC project, and our objective is to build a pilot system incorporating as much European technology as possible. So the system itself is not ready, but we are working not just on hardware. Actually, we work a lot too on software and on applications, which is why we decided to start a series of webinars about what we are doing in this respect, about applications and software stack. So I have put here the program, the list of upcoming webinars. As you can see, there will be one in January, and registrations are already open for Open Gadget in January, on the 28th of January. So if you're interested, go to our website or go to the list of webinars. The link is here, and you will find the link to register. So now let's go to today's topic. So today's topic is Bolt65 AI Fusion, a case study in object detection, and I'm delighted to welcome Hannah Ivanchik. First of all, I'm delighted to welcome you because at last we have a woman speaker. I mean, there are not many of us in HPC, so I'm really very happy to have you today. So Hannah is research and teaching assistant and PhD student at the Faculty of Electrical Engineering and Computing at the University of Zagreb. And I know her fan club is here too. So hello, everyone. So Hannah is going to talk about Bolt65, and I will let you introduce this topic. So just one word before I hand over to Hannah. We will take your questions at the end of her presentation, and I will send the slides to all attendees. So I promise I will send them after the webinar. Okay, so Anna, if you can share your slides now, I will stop sharing.
Okay, thank you.
And the floor is yours.
Can you see the slides?
Yes, but you are not in slideshow mode yet.
Okay.
Yeah, now it's fine.
Okay, great.
Good.
So we can start. I would first like to thank everyone for joining today. As Pascal mentioned, today I'm going to introduce an application developed here in our HPC Architecture and Application Research Group at the University of Zagreb. First, I'm going to shortly introduce the Bolt65 video transcoder and explain our motivation for the integration of AI into it. Then I'm going to talk about the YOLO network, which is the network we used to test the AI integration and use it for object detection. And finally, we will talk a little bit about the developed framework and how we integrated it into Bolt65. So Bolt65 is a performance-optimized suite for just-in-time video processing based on HEV's standard. It consists of three main parts, which are encoder, decoder, and transcoder. The encoder part is responsible for encoding raw video to HEVS format. The decoder works in the opposite way, so it decodes the compressed format of the video to the raw file. The transcoder is actually a cascade of both of them. So the video is firstly decoded from one HEVS format to the raw pixel values, which are then again encoded, but this time with some different properties such as the spatial resolution or the frame rate. We developed Bolt65 in plain C++, so it doesn't depend on any external libraries, which makes it perfect for the exploitation of different architectures and low-level optimizations. We ran and analyzed Bolt on several video sequences. Here on the right, you can see 9 sequences that we selected with different resolution, number of frames, and frame rates. Sorry, I skipped a slide. I'm sorry. So we implement the Bolt and analyze it first on different platforms. Here we use the corresponding intrinsics for each one of the architectures. We used SV intrinsics for ARM-based architectures, EPI-RISC-V for RISC-V, and AVX for Intel. We also used different compilers, and these tests were ran on the encoder because it is more complex than the decoder, and as the transcoder is consisted of both the encoder and the decoder, the results will also be relevant for it. We defined 4 different implementations. The first one is a scalar version, which has no vectorization. The next one is auto vectorization, where the compiler automatically vectorizes the code without us changing it. Then the third one was manual vectorization. We identified the kernels, the functions that that are the most complex and use the most of the coding time, and vectorize it for different architectures. And the last version or implementation is both auto and manual vectorization. It differs from the previous one because the manually vectorized kernels are still used, but apart from that, we also use the auto vectorization to vectorize the other parts of the code. So now the test sequences, as I said, so they have different resolution, frame rate, and number of frames to be able to test the encoder in different circumstances. So we defined 3 base use cases. They differ in the way they predict the pixel value. So instead of encoding the raw pixel value, we actually try to predict its value and then just encode the residual, so the difference between the original pixel value and the predicted one. The first way we can predict the pixels is using intra-prediction. This way of coding tries to predict pixel value based on its neighboring blocks. And the other version is interprediction, where the pixel value is calculated based on previous frames and motion estimation. So the first use case is all intra-prediction, so all the frames use intra-prediction. And in other 2 cases, we use both intra and interprediction. In the lower computational complexity use case, some of the frames use intra and some interprediction. None of them use both of the options at the same time for the same frame. This type of encoding has a bit lower quality, but it's faster. And it is used in cases like in real-life cases where we need to encode the video fastly. So, for example, now like video conferences, we must encode the video pretty fast and don't spend a lot of time to on the quality of the video. It just has to be good enough. And the other version is higher computational complexity. In this case, some of the frames use both intra and interprediction. In these cases, the video is pre-encoded and stored on the server. So it's not encoding in real time when we need to use the video. Okay, so in order to vectorize the kernels that use most of the time, we used two different profiling tools. On the ARM architecture, we used Perf Profiler, and on Intel, we used VTune Amplifier. Here we can see that the results are a bit different. On Intel, we spend a bit more time on functions that access the memory, like fetching the blocks or filling them, but the other functions are the same in both versions. So the most of the time is spent in multiplication or sum of absolute differences. So this is how we decided which kernels we will vectorize. Here on the left, you can see that we also vectorized the discrete cosinus transformation and its inverse. Even though they do not appear here on the charts on the right, they are the only ones who use this multiply function. So by vectorizing them, we resolve this problem here with the blue part of the chart. We also vectorized intra-prediction kernels because for each intra-prediction, we test which one of the possible predictions has the smallest error. Okay. Here we can see the results for different use cases and different architectures. So in the first case, we have the previously described all intra frames, then low complex and high complex. This graph shows their speed up in comparison to the scalar version. We can see that the auto vectorization has lower speed than the manual one. When we use both of them, the speed is a bit higher, but the results are not significantly different when using only manual vectorization. We can also see that for RISC-V architectures, the vectorized version, when using only auto vectorization, is even slower than the scalar. And that is because of RISC-V's current lack of optimization for operators with different operand size. So here in Bolt65, we often change between 8, 16, or 30-bit elements, 32-bit elements. And now I'm going to talk a little bit about what motivated us for AI integration. Well, we actually wanted to be able to port Bolt65 to edge devices such as smart cameras. This way, we could run the object detection directly on a camera and then send only the important part of the data to a server. Usually, if we cannot port the object detection to the device, we have to transmit all the video data to a server and then there perform the object detection. This way, we could make the data transmission smaller and improve the performance. Of course, our first step was to look at the existing solutions. The first one was OpenCV, a popular library. It's a really fast and easy to use solutions. The functions are optimized and you get the output really fast. But our problem with it was the library size. the library was too big and we wanted to use just a little part of it. Also, it was not really easy to customize because of the fact that all the functions are already really optimized and you can't see easily the details. The other solutions were some open source ones. The problems with them were that most of them were written in Python, and the ones that were written in C++ highly depended on the external libraries. This way, we could not port it that easily, and again, we couldn't customize it as we wanted to. Then our next step was to investigate the model structure. Just as OpenCV, we decided to use Open Neural Network Exchange. This is an open format for representing machine learning models. It defines the set of possible operators, standard data types, and computation graph model. So each network is represented as a graph where a certain node is an operator. Its output is the input of the following one or several nodes. Here on the left, we can see an example of this ONNX graph for YOLO network. So in the input, we can see the image tensor with dimensions 3 like RGB pixels and the dimension of the image. Then we pass this tensor through all the nodes of the network, and in the end, we get the output, which here is the maximum number of detected bounding boxes and the data for each one of them. Our idea when we saw this graph was to implement these necessary operators in C++. As you can see, they're quite repetitive, so we didn't have to implement so many different operations. Just like in Bolt65, we decided not to use any external libraries and just write the model and build it as a series of functions, which would then again be customizable. Okay, now the YOLO network, I showed you a little bit on the previous slide, but this is the network we decided to use for object detection. So it is a one-stage object detection algorithm. That means that in a single stage, in a single pass, it localizes, so finds the object on the picture and classifies it to one of the predefined 80 classes. It consists of, well, many layers, but two main parts. The first one are the convolutional layers, which are responsible for feature extraction, and then later fully connected layers, which detect the bounding boxes and predict the class probabilities. This is a simple architecture of the first YOLO version. The YOLO 7 is a bit more complex. Here, I put an example of the YOLO network output. So the output of the network are those bounding boxes. We have a predefined maximum number that can appear on an image. The first value of each bounding box is the confidence that an object was detected. The next four values are the dimensions of the bounding box, so the x and the y center of the object and its height and width. And the remaining values are the class probabilities. So with how much confidence we can say that a certain object is part of some class. So here on the left, we can see that the image is divided into cells, and each cell is responsible for detecting the objects that fall within it. So here, the purple cell, we can see that there are no objects within it, so the confidence is 0. So the rest of the values are irrelevant for us. In the other two cases with the green and the yellow cells, we can see that the confidence is 1, so the object was detected. And now these next bounding box values have some meaning. So as I said, the Bx and By are the center of the element, but within this box, while the height and width do not depend on a specific cell. Here, in both cases, the class is a car, but of course, this is a bit simplified version. A class can have probability which is higher than 0 or lower than 1, but we select the class with the highest score, and of course, which is higher than a threshold we set. After performing the object detection, if an object falls into several cells, we can have a problem of multiple detection of a certain object. So here on the left, for example, we can see that this car was detected multiple times. I don't know if you see on the left, like various boxes were plotted here on the same picture. And to handle that, we run a non-maximum suppression algorithm. The algorithm first sorts the detected boxes depending on the confidence that an object was detected in the descending order. It takes the first detection and selects it as an accepted one. And for each one of the remaining bounding boxes, it calculates the intersection over union with the already accepted boxes. If the intersection is lower than the threshold, then the detection is accepted as a new bounding box, as a new detected object. In the other case, the detection is discarded. Here on the right, we can see that after running the algorithm, we have a single box for a single object. And now the model inference framework we developed. So as I previously described, we decided to use ONNX network, which is organized as a computational graph. We serialized it and performed graph traversal, where we visited each one of the nodes and called the corresponding operator without, of course, using any external libraries. Currently, we support EUPEX, JPEG, and PPM inputs and outputs, and our framework is configurable, so the user can set a network he wants to use, the thresholds for different objects or the intersection over union, and the user can also select which classes he wants to detect. So here on the right, we can see a simple example. In the bottom picture, we detected a fork, knife, a spoon, and a glass. And on the upper one, we also detected a plant. So here the user decided that these are the only classes he wants to detect, even though the other objects do appear on the image. But here is a little workflow diagram of the framework. So after configuring the parameters, we must first initialize the model. We first read the attributes from the model definition. These attributes are necessary for calling the operators for each node. After we have read them and prepared them, we can then get the model nodes and now set the input image. When preparing the input, we must, after reading the image, prepare the pixels. So the network receives an input of raw image pixels in RGB format. So if we have a JPEG image, for example, as the input, we must first decode it to get the raw values. Then the next step is to resize it to the expected size. If the picture is not as the model expects, we must scale it to that dimension and then later return it to the original size. And now, as the last step of the pre-processing, we put the input image tensor on the model input. Then we run model inference by calling the operators one by one until we get to the output node. After getting to the output node, we can run the non-maximum suppression on the detected boxes, plot them to the original image, of course, resize it to the original size, and store it to the output. Here again, we can select whether we want to save it as a JPEG or PPM or UV file. This is the list of currently supported operators. So now the framework can parse any network that is consisted of these 18 operators. Some of them are really simple, like addition, subtraction, or logical operators. Some of them change the tensor dimensions, such as reshape or transpose. And the yellow ones are the most time-consuming and complex ones, and they are convolution, max pooling, and resize. All of these operators are ran on tensors, so it makes sense to vectorize them because they're repeating for each of the element of the tensor. The advantages of this framework are, of course, the independence of external libraries and portability to different architectures. We could also easily update the framework to add some new operators, and this way to make it to also support some new networks. Also, as the code is written in C++, it is easy for vectorization. The disadvantages are that it is currently slower than the OpenCV version, and of course, it doesn't have the community support as those big libraries do have. And now the last step of our project was to integrate this framework into Bolt65. So here on the upper image, we can see the normal Bolt65 transcoder without any object detection. So the input is the Hefts encoded video stream, which then enters the decoder. In the middle, we have the raw video file stream, which then enters the encoder, who encodes it into, again, Heft's video stream, but with some different properties. So as the model inference takes the raw image pixels, this part where we have raw UV stream is the ideal one for model inference. So instead of passing the Heft's decoder output directly to the Heft encoder, we first pass it through the model inference. This way, we must first, of course, transform the pixels from UV format to PPM, then run the model inference, and then again return it to the UV format and pass it to Heft's encoder. Heft's encoder then doesn't see any difference in the input from before because the boxes are plotted directly on the original stream. Here is a short demo of the detecting objects on a video. This is in front of our offices, and we selected that we want to detect different vehicles, so cars and trucks. As you can see, it successfully detects all of the vehicles that appear in this video. And for future work, we would like to upgrade the current framework by introducing first batch processing. Currently, each frame is passed through the whole network one by one. But if we include batch processing, then we could run several frames at the same time through the network. One of the next step is also the vectorization of operators for different architectures. So SVE for ARM, EpiRISC-V for EPI, and AVX for Intel. and of course, to run the performance analysis, just like we did on Bolt65. And that would be it. Thank you for your attention. Here I put some links if you would like to find out more about our group. And if you have any questions, I would be glad to answer.
Thank you, Hannah. Sorry, I'm trying to switch my video on. Yeah, now it's on. Thank you very much for this presentation. So if I will share my screen again. If you have questions to Anna, please ask your question in the chat, or you can raise your hand. It's really up to you, whatever you prefer. Actually, I have a question. I'm not sure you have the answer, Hannah, but I will.
I'll try.
No, I mean it's not technical. You know, it's I'm the EUPEX exploitation manager, and it's the exploitation manager asking a question. I mean, what kind of uses are you planning for this new Bolt 65? Is it going to be open sourced, or maybe is it could it be integrated in a commercial product? Do you have any idea what's going to happen to this application?
Well, I'm not exactly sure, but the idea
Yeah.
is to make it useful for different applications. So the framework can parse different networks. They don't have to be only for object detection. So
Okay.
we modify it for different applications.
Okay. So in theory, many possible exploitations of this.
Yeah.
Yeah. Okay. Do we have questions in the audience, please? If I displayed the chat, maybe I would be able to see questions in the chat.
Yeah, I
Sorry.
see two of them.
You see the chat because I don't see it. Ah, sorry.
I can answer the first one. So
Okay.
is the ONNX
Oh,
model.
okay. Yeah. Relation between YOLO and your ONNX model. Okay.
Okay, well, the YOL network is presented as an ONNX model. ONNX is just a format. So it can present different architectures. That is just a graph that represents a certain network. And the other question was if the model is parsed in C++ or in Python. Well, everything is in C++. We don't use Python in any part of the code.
Okay. Oh, Jean-Robert. Maybe touch base with Evidence computer vision team based in Grenoble for potential collaboration. Yeah, good idea.
That would be great.
Yeah, that would be great. That was exactly the point of my question. So yeah, that would be nice. Okay. Any other question? No? Come on, don't be shy. Is the code base open source? Oh,
It's not
it's
yet,
not.
but I'm not sure if it will be.
Okay. 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 Did you write the model from scratch or based on YOLO?
This is exported from YOLO 7, so the PyTorch version of the model was exported to the ONNX from format directly from their GitHub. So we didn't write the model from scratch.
Okay. Okay. So Jean-Robert proposes to organize a meeting with the Evident teams when we have our project face-to-face meeting in February. So that's wonderful. Okay. Any other technical questions? No? Okay. Anna, is there anything you wanted to add about this or no?
That's it.
You
Thank
said it all already?
you.
Okay. Well, if there is no more question, then we will stop the webinar now. I'll give you 20 seconds to ask another question if you have one, because, you know, I know some people are shy and usually they hesitate. No? Okay. Okay, then I put the link to for the registration for our next webinar in January. It will be about Open Gadget. So if you enjoy our webinars, please register. So we'll move to a completely different area. It's about astrophysics, Open Gadget. So completely different. So thank you very much, Hannah, for this presentation. Thank you for sharing your work with us. This webinar was recorded, so if you want to share it with other colleagues, it will be on the EUPEX YouTube channel. And finally, I would like to thank our audience. Thank you to your cheerleaders in Zagreb. Hello, everyone. It was nice having you on board today. So bye-bye, and hope we'll talk to you again in January for our next webinar. Thank you.
Thank you.
Have a nice Christmas season.
Thank you, Jean-Robert.
Yeah, it's coming now, so it is the last webinar
it's
of the
true.
year,
It's
so we can
Christmas
wish
soon,
ourselves,
so
yeah, all the best.
I hope everyone enjoys this end of the year, very special holiday season. Bye.
Exactly. Bye.
Bye.
Thank you. Bye-bye.
Thank you. Bye bye.